Hi. So far in Class 7, we've looked at the thermodynamics of enzyme catalysis and also went over some ways an enzyme can lower the activation barrier. In this video, we get to look at a mechanism finally and see how an enzyme pushes electrons to help catalyze a reaction. The enzyme we'll be looking at specifically is HIV Protease, which uses a general base and general acid mechanism, and it uses this mechanism to mature the HIV. This is the ribbon model for HIV protease, and there are several things that I want y'all to know. HIV protease is a cleavage enzyme. It's an aspartyl protease. Those are your two aspartic acid residues that are involved in the mechanism. It operates via a general base, general acid catalysis, and we'll see details of that soon. And it is effective at stabilizing the transition state to speed up cleavage of a polypeptide. And it actually cleaves this polypeptide, which we'll see in just a bit, at 9 different sites. The proteins that HIV cleaves, or HIV protease cleaves, is GHG and GHG-POL. And when those proteins are cleaved, the mature protein components of the HIV variant is made. Variant meaning it's the infectious form of the virus outside of the cell. In this schematic, we have the protease shown right here. And it's within the immature HIV envelope. But once it does its cleavage of these two proteins, the HIV variant is matured, and now it's infectious. One can imagine that if you can stop or inhibit this protease in particular, that you can slow down or even stop the infection rate. Before we take a look at the mechanism of HIV protease and how it uses those two aspartic acid residues to catalyze the reaction, it'd be good to go over the 4 types of catalysis that deal with acid and bases. The first one we're going to look at is specific acid, then we're going to look at general acid, then specific base, then general base. Just keeping in mind that, do I have it here? That HIV protease is going to be a general base, general acid catalysis mechanism. Let's take a look at specific acid catalysis first. We want to remember that the proton has been fully transferred to reactant before the rate determining step. I'll do a very simple reaction. Let's try this. What are we doing here? We're going to attack this ester. Okay, so it's the beginnings of hydrolysis. So here we have the proton has been fully transferred to the reactant. Let's use, for instance, HCl. Okay, so there's your transfer. Nothing special. This is how you would hydrolyze an ester anyway, using specific acid. In this case, HCl, but you've seen it done with H2SO4 and H3O+. And then we have our slow step. Right, the slow step is the attack of this carbon. We'll call this maybe the RDS. And what's happening? We have water. And the attack is the slow step. Typically, proton transfers are very fast. And that is not the full mechanism, but it shows you specific acid catalysis. Something that you're very familiar with. In contrast, general acid catalysis, the proton is transferred to the reactant during the slow step. This is something that most people taking organic chemistry do not see. And this is what happens within the enzyme. An example, again, we're doing a hydrolysis of an ester. This is how you would normally do it in organic chemistry. But the enzyme typically uses general acid catalysis, and that would look like this. Here's your ester. And we are going to use, I should write here, weak acids, like carboxylic acid, or maybe a protonated amine. Let's use that protonated amine actually. During the slow step is when the attack happens, when water attacks. So this is something that I would never see teaching in an organic chemistry class. But when we're looking at enzymes, this happens. How should we draw this? Either you could draw the bond to the hydrogen like this, or in some textbooks they draw the bond to the atom and then they use a lone pair. But I'll do it this way. So do you see how the proton transfer is happening at the same time when the water attacks? That is the RDS. And do we get the same result? Yeah. We get the same result as we did with specific acid catalysis. Next will be specific base and general base catalysis. Specific base catalysis, the proton is completely removed from the reactant before the rate determining step. See, very similar to specific acid, where the proton was completely transferred before the rate determining step. Here we'll use a strong base, and we are going to again do the hydrolysis of an ester, but for the specific base catalysis, we are going to first completely remove a proton from one of the reactants using in strong base. I'll just use hydroxide. And do you remember what the rate determining step is in a hydrolysis? It's the attack of the carbonyl carbon. So I have that, and then next, in the rate determining step, we get the attack of the ester. Make the tetrahedral intermediate. Okay. Actually, I don't think we're doing a hydrolysis. We're doing a what are we doing? Maybe a transesterification. Maybe I should change this then. Make this a different R group. Okay. Yes, this will be transesterification. But the more important thing is that we fully deprotonate one of the reactants before the attack, which is the rate determining step. You can imagine that in the general base catalysis, we don't get complete removal of the proton, and probably at the same time the rate determining step happens, that's when we remove the proton. Let's try to come up with an example of general base catalysis. Let's take our same ester. Our other reactant was this methanol. But now we're not going to deprotonate this before the slow step. It will be during the slow step. You should use a weak base. Let's try this. NH3 neutral. Okay, we grab that. Again, you could either push these two electrons onto the atom and then use the lone pair to attack. Just like before in the general acid case, I'll use the bond and do that. And we have that. This is the slow step because it is the step where we have the attack. And again, are we getting the same product as the specific case? Okay. Do you see the comparison between the specific and the general? And just make sure you see the difference between the specific and general for the acid catalysis. Very analogous from A, B, C, and D. Let us apply this to HIV protease. It is a general base, general acid catalysis or enzyme. How I have this set up is that here is the peptide that is going to be cleaved, and here are your two aspartic acids. One is protonated, one is not. They're actually aspartic acid 25, residue number 25, because there are two subunits. So these are two different subunits that are coming together, and in each of the subunits, aspartic acid occurs on the 25th residue. We are going to show general base catalysis at the beginning. Meaning that we're not going to fully deprotonate the reactant before the RDS, we're going to do it during the RDS. Remember how to do that? We grab this H. Let me do it a little bit different than how I showed it on the previous pages. Let me show how some textbooks do this. They push that bond to the atom, and then they use that lone pair to attack. You know how we were doing hydrolysis in our examples? Same idea. We're attacking that carbon, and we're creating this oxygen anion. Okay, after the first step where general base catalysis happens, the resulting substrate is a tetrahedral intermediate. Let me write that down. But then as it progresses in this reaction, it becomes a transition state. And this right here, we're going to say that that is stabilizing the transition state. So this is a very important part of the enzyme. We get transition state stabilization. So that second aspartic acid is very important. This one right here. Next, what happens? We're going to do general acid catalysis. So we're ready to go on to the next step. Using general acid catalysis. And what is that? That is, you don't fully protonate before the rate determining step. You actually protonate during the rate determining step. So what's going to happen here? We are going to have this bond reform, okay? And we're breaking this peptide bond, right? And I'm going to push these electrons onto the nitrogen. Do you see how we did not fully protonate this nitrogen before this step? Because we're protonating it during this step. So that's where the other aspartic acid is coming into play. And we're going to regenerate, right, the deprotonated aspartic acid here. And the enzyme will be ready to go again. Why don't you try to draw the result? Okay, draw the result and double check against my drawing. Okay, what's happening here? We get the cleavage right away. in this second step, and we have the two pieces of the protein. The peptide bond has been cleaved, and also the enzyme is ready to cleave another peptide. What was important here is that we know that what general base catalysis and what general acid catalysis looks like. And in the previous video, we made it a point to say that enzymes bind the transition states best. So it's not really the binding of the peptide that is energetically favorable. The enzyme is set up to stabilize the transition state. That is what really speeds up the reaction. And when you stabilize the transition state, ultimately you are lowering, as we saw in the previous video, delta G, not double dagger.